Okay, so today we start our lesson on sinusoids and the engineering applications of those. And so to think about this, we return back to the one-planar robot. So we talked about this with 2D vectors. The one-link planar robot, we've got a fixed point at the origin, and the robot's able to rotate a single arm around here. And we developed some equations that allowed us to relate the length, or the point at the end of the robot, to the angle that it makes with the x-axis and how long the robot arm is. And so we'll take those into account. And so right now what they say is happening with the one-link robot is, suppose it starts at 0 degrees, and then it begins to rotate at a constant rate. So it starts going around at a constant rate in a circle. And of course I'm not real good at doing things constant, so you might find that that's not exactly true in our case. But yeah, suppose it takes 2 pi seconds for it to make one full rotation there. That the time to go from 0, go all the way around back to 0 is 2 pi seconds. And why would I choose something like 2 pi instead of something simple like 5 seconds? Well, because it will really start to make sense once we start to kind of break that down. Because the other thing we want to think about is, again, that we're trying to think of x, and we want to plot what x and y are in terms of the time. We don't have something that relates it to time, but what we end up doing is, if we say that it takes 2 pi seconds to get all the way around, and that's also going, our angle is changing 2 pi radians, then I know for every second I'm moving 1 pi radian, which really helps me simplify my graph. So that's where we want to start with this. And so we set up our engineering paper. So the return the one-link problem, part A. So we're given that the robot starts at an angle of 0 degrees, rotates at a constant rate, that the time for a full rotation is 2 pi seconds, and then we want to plot x and y for 0 to 2 pi seconds, for the time going from 0 to 2 pi seconds. So yeah, big T will be our total time to rotate. T is time since rotation started. So some key factors that help me work that out is, as I just said a minute ago, we're going to use the fact that because it's going, that theta for one rotation, theta goes from 0 to 2 pi radians. And time goes from 0 to 2 pi seconds. So knowing that that is moving at that constant rate, that means that theta in radians equals the time in seconds. So that's going to be really helpful for trying to create our plots, because we know that at any given point, if I start rotating this, that the x component, we drew a quick little triangle, that the x component is cosine times the length, or length times the cosine of theta. So we remember x equals L cosine theta, and y equals L sine of theta. And that was true all the way around the board, all the way for one full rotation. So we use those equations. If we can use that theta is equal to t, then I know that what it looks like is that x is going to equal L. I didn't really define my variables there. L is the length of our link. We don't know exactly what that is. We're just going to keep that as a variable. So L is our length. So we can actually rewrite these in terms of the time variable. That y, because this is true for our particular case, we can replace those. And so I have these two functions that I want to graph. And so, again, I'll just use kind of generically. So this one, we will plot one, two, three, four. Yeah, that'll give me a good breakdown. So on this one, I'll have x of t, and my axis here is t. And for this one, and I'm going to do my best to keep them one on top of the other so that we can track them together and everything lines up. Sorry about that, it jumped a little bit. Yeah, so we have these two, and this one would be y of t versus t in seconds. And so my top point on each one of these would be L. And negative L. Make sure I've got the same number of blocks each direction. All right, so if we think about our plot. So we start out at time 0, we're at angle 0. We know that the x-coordinate is all the way out to L. And the y-coordinate is at 0. Gotta clean that up. All right, and so just in terms of simplicity, let's go ahead and move to 90 degrees. So if we move it all the way up this direction, then 90 degrees, I know the x-coordinate is now 0. And so, but remember, what we're thinking about is radians, not degrees. So if I do it in terms of degrees, this point is pi over 2 radians. And at pi over, I'm going to have to change where my label is just to, it'll fit better. Pi over 2 radians, we're at 0 there, and my y is all the way up at L. So we've got those 2 points. I keep going, rotate it another 90 degrees, or another pi over 2. So now I'm at an angle of pi, 180 degrees, and of course at that point, again, my y-coordinate is down to 0. So at pi, I'm down to y-coordinate at 0. And for this one, at pi, my x-coordinate is all the way to the left, so it's in the negative region, and it's at a length L. Keep going, do the next 90 degrees. So again, we're kind of getting the hang of this. That's 3 pi over 2. We're back to 0 in the x direction. At 3 pi over 2, we're at negative L in the y direction. Do one more rotation back to here. So at this point, we're at 2 pi. We've made a full rotation. We're all the way back to the x-coordinate is L, and the y-coordinate is 0 at 2 pi. So, of course, I could fill in all the points in between by taking, I can do 45 degrees, which is pi over 4, and figure out what that number is. But I can certainly see that it's, I would use the same relationship. I would use the same function, that it's the sine is for the y value and the cosine is for the x value. And what we would see is we get a picture that looks something like this. And this is where my sketching gets unfortunately bad. But yeah, you've probably seen what a sine curve looks like. It's generally just kind of a wave-looking thing. It kind of curves down there, and then it'll switch, and we'll curve it down to our next point. Curves back to 0, and on to there. Again, if we had used the graphing utility, use your calculator, or something like that, we could just plot L times cosine theta for the x and L times sine theta for the y. So yeah, remember this is L cos of t, and this is L sine of t. And so this one, yeah, we curve up until we get to 1, or until we get to the length. Is all in the y direction. Then it kind of, well, again, this is where I said, me drawing this is not your best utility. It kind of curves back there. So we would curve back down to 0. When we get to 180 degrees or pi, we curve it back that way. And then it would curve back up there. And so both of these are what we call sinusoids. Or they're also called harmonic signals. And with these things, we have certain properties that we recognize. One is that they'll repeat. So if I kept going, if I kept going out here to the next one, if I got to 5 pi over 2, so if I kept going, I made one rotation around. If I kept going and got to 5 pi over 2, I would be back there again. So these just keep repeating. So maybe I'll just make a little table over here, sorry. We call the amount of time it takes for it to complete one turn around the period. So it's kind of the time between repeats. So we set up in the beginning that we want it to take 2 pi seconds for it to make a full rotation. So that actually is the period of this if it's 2 pi rotations. The amplitude, it's how high or low. So for this one, it goes as high as L to negative L. So the amplitude is L. And there's some other things we'll work out in the next video and really break down what we're doing here. But one of the main things is just kind of see where these harmonic signals come from. They're used in many different applications, as we'll see in future videos.